All right, class. So today we're gonna move forward. So last lecture, or the last set of lectures that we should have covered or that you should have looked at, we went over the different types of electrophilic aromatic substitution reactions you can do. And this was just starting from benzene. Well, now what we're going to do is we're going to see what happens when we start with an aromatic compound that already has one substituent on it. And there are two considerations that we have to have when we're starting with a monosubstituted aromatic ring. The first one is how fast is the reaction compared to benzene. So, for example, if I start with toluene, the question becomes: is the reaction of is the nitration of toluene faster or slower than the nitration for benzene? And so that's what we call the rate of the reaction. So a substituent on an aromatic ring can affect the rate of the reaction. And it turns out that if I have in terms of this reaction here, if I have an alkyl group on here, that toluene reacts faster than benzene. And the reason is because we say that the toluene, the CH, this alkyl group, is electron donating, making this aromatic ring a better nucleophile. The better this is a nucleophile, the faster that first step is. Remember, there's two steps: the addition step, which makes the carbocation, that's the rate determining step, and then the elimination reaction to reestablish aromaticity. So when you have this alkyl group on there, this reaction is actually faster than with benzene. The other thing to consider is, where does the nitro group go? So if you think about it, when I do a nitration on a mono-substituted ring, I could add to the ortho position, I could add to the meta position, or I could add to the para position. Where the next group goes is called the regioselectivity of the reaction. And so we're going to look at where that next group goes. It turns out that because the alkyl group makes the reaction faster, we call the alkyl group an activating group. So an activating group is something that makes the reaction faster compared to benzene, right? So this is an activating group. And then when you have the activating group, what we find is that if we look at the different products that are made, the ortho versus the meta versus the para, you make predominantly the ortho and the para product. And so what we say is, and you make very little of the meta product. And one of the questions becomes is, why do you get predominantly the ortho and the para product? So when you get something that just makes the ortho and the para product predominantly, we call that an ortho para director. Okay? So this alkyl group is an activator. We call this an activator. And this particular activator, so that's the rate of the reaction. That means this is going to make the reaction faster than with benzene. This group is also an ortho-para director, which means you predominate the ortho and the para product. And one of the things we want to think about is, well, why do we get predominantly the ortho and the para product? And to look at that, what we have to think about are the stabilities of each of the sigma complexes that form from each different reaction. So for example, if this double bond attacks here and I'm going to add ortho, if that double bond attacks there and I add ortho, the first resonance structure you would make would look like this. If this double bond attacks here and I add meta, what you make is you make this. You make this carbocation. And then if this double bond attacks that nitro group there, and the nitro group ends up adding para, that's the intermediate I make. And what we find is that the reason why the ortho and the para products are going to be formed more is because these two intermediates are going to be more stable than the meta intermediate. And to see that, what you need to do is you need to draw the different resonance structures of each of those intermediates. So take a second, why don't you pause the video now, and why don't you try to draw the different resonance structures of each of these intermediates, and then look at those resonance structures and try to determine why the ortho and the para intermediates are more stable. Okay, so welcome back. And so if you did that, you should have ended up with 3 resonance structures in each case. And if you look at each of these 3 resonance structures, what you notice is that for the ortho and the para intermediates, that the carbocation ends up at the carbon with the alkyl group on there. So each of these intermediates have a tertiary carbocation in their resonance structure, whereas the meta intermediate does not. So what that means is that the sigma complex for the ortho and the para intermediates are more stable, they're lower in energy than the sigma complex of the meta intermediate, meaning that the rate to get here is easier, and so then you form more of those products. Now, one of the things to kind of go back and look at is that, like in this particular case, you get more of the ortho product than the para product. And the reasoning here of why it's thought you get more of the ortho versus the para is because there are 2 ortho positions compared to the 1 para position. And you kind of see that, right? It looks like there's double the amount of the ortho intermediates versus the para intermediate. Now let's look at another type of activating group. Let's look at what we call the methoxy group. So the methoxy group is an oxygen bound to a methyl group. And what we find here is that the methoxy group is even more activating than the methyl group. That reaction is 400 times more reactive than benzene. It's way more reactive than toluene. And the reason is that the methoxy group is thought to be electron donating via resonance. Remember, when you have oxygen, one of the peculiar things of these things is that the oxygen can be donating via resonance or electron withdrawing via the inductive effect. And most of the time what we find is that the resonance effect of these atoms of oxygen and nitrogen, they usually win out. So the oxygen is electron donating. So I'm going to donate down here. And what you see when I donate down there, you end up having this negative charge being moved around the aromatic ring. And notice where the negative charge actually ends up. This is going to become important in terms of the regioselectivity. Notice that the negative charge is ortho here, para here, ortho here, never meta. So the methoxy group is a very strong activating group. And in fact, the methoxy group is such a strong activating group that you don't even need a Lewis acid a lot of times to get these electrophilic aromatic substitutions to react. Like if I take the methoxy group and I react with an excess of bromine, I will actually brominate 3 times, ortho and para. And so what we find is that the activators, and this is a trend that we will always generally see, activators are ortho-para directors. And so in this case, you make more of the para product than the ortho product, because what's thought to happen is that this methoxy group is thought to be more sterically hindered. So this methoxy group is thought to be fairly big, blocking these 2 ortho positions, right? And so you get more of the para product in this case. And the reason, again, the reason why, and for something like methoxy, the reason why the ortho and the para intermediates are more stable is because those intermediates are resonance stabilized. So if you look at the intermediate form from the ortho attack, the carbocations here, I move the double bond around like with the alkyl group, but then there's one final resonance structure where the electrons kick down from the oxygen into the aromatic ring to give you this additional resonance structure, which you see here. And remember, anytime you can draw more resonance structures than something else, that usually makes that thing more stable. And so this is just the reaction coordinate diagram showing you the difference between these 2 things. And again, it actually shows you that the para intermediate is slightly more stable than the ortho intermediate due to sterics, right? So this NO2 being further away from this kind of slightly bigger group makes this slightly more stable than this group here. All right, so that's activators. So I hope that made sense. Let me know if you have any questions on what makes something an activating group and what makes those activating groups ortho-para directors. Thanks, and let me know if you have any questions.